All right, let's dive into something that's happening inside your computer right now. Something you probably never even think about. We're going to talk about a secret hero, this invisible valet that's in charge of your computer's memory, a silent operator just working at lightning speed to keep everything you're doing running perfectly smoothly.
I mean, have you ever stopped to think about it? Right now, you might have, 50 browser tabs open? You're on a video call, maybe a game is running in the background. You're asking your machine to do 100 things at once, and somehow it just works. It doesn't just crash and burn. Well, that seamless multitasking, it's not magic. It's all thanks to this incredibly sophisticated system called memory management.
So let's start with what I like to call the memory puzzle. How in the world does your operating system solve this fundamental problem? Fitting a constantly changing number of programs into a very, very finite amount of space.
Okay, so what is memory management? At its core, it's really all about control and coordination. You can think of it like a traffic cop or maybe an air traffic controller. But the analogy we're really going to run with today, it's the valet parking attendant for every single process running on your system.
So yeah, let's really stick with this idea. Imagine your computer's RAM, that's random access memory, is like a super premium, high-speed parking lot right next to a big event. It's the best spot. It's where all your active programs, our cars, need to be parked so they can run really, really fast. The catch? The lot isn't infinite. And that memory manager, well, that's our valet, and it's their job to figure out exactly where every single car is supposed to go.
So how did the first valets handle this job? You got to imagine the early days. Let's take a look at the first, and honestly, kind of clunky attempts at solving this whole problem. Okay, so the very first approach was, well, it was the most obvious one. If a program or a car needs a 10 kilobyte spot, you just find an empty 10 kilobyte chunk of memory, and you stick it right in there. Simple, right? This method has a name, it's called contiguous allocation, and it just means every program gets one single, continuous, unbroken block of memory.
Now to make this work, our valet had a few different strategies up their sleeve. There was first fit, which is exactly what it sounds like. Just grab the very first spot that's big enough, done. Then you had best fit, which was a little more careful. Find the snuggest possible spot to waste as little space as possible. And then there's worst fit, which sounds weird, but it tried the opposite. Put a small car in a huge spot, hoping to leave another big useful spot behind. But you know what? In the end, it didn't matter. They all ran smack into the exact same inevitable problem.
Yeah, just think about it. What happens in a really busy parking lot? You've got cars of all different sizes parking and leaving all day long. A huge SUV pulls out. A tiny little smart car takes its place. Then a sedan leaves from over there. After a few hours of this, what does that parking lot start to look like?
You end up with a total mess. This right here is called fragmentation. And it is the Achilles heel, the killer flaw of that whole contiguous allocation idea. And it comes in two flavors. On the left, you've got internal fragmentation. This happens when you put a program into a spot that's just a little too big for it, so you're wasting space inside the parking spot. And then on the right, you have external fragmentation. This is where you get all these tiny little useless gaps between the parked cars. You might actually have enough total free space to park a new car, but none of it is in one single chunk. It's all broken up.
So you can see how this fragmentation thing was a massive headache, right? It just made the whole system super inefficient. To fix this, they needed a completely new way of thinking about the problem, and that led to what we called the paging revolution.
And here is the absolute genius idea behind it. What if you forget about trying to find one big spot for the entire car? What if our valet could just break the car into equal-sized pieces and then park those pieces in any open spot? Put the wheels over here, the engine over there, the doors way back in that corner, and just keep a perfect map of where everything is. It sounds totally nuts for a real car, but in the world of computer memory, it's absolutely brilliant.
And that's the core of paging. The official definition is that a program is broken into these fixed-size blocks we call pages, and the physical memory, your RAM, is also broken up into blocks of the exact same size, and we call those frames. So now, any page can be stored in any available frame. And just like that, the problem of finding one big continuous spot is completely gone.
So you're probably wondering, how on earth does the computer keep track of all these scattered pieces? Well, it uses something called a page table. And this is basically our valet's master map. Here's how it works. The CPU says, I need some data, and it generates a logical address. Now this address has two parts. The first is a page number, let's call it P, that tells the system which piece of the program it wants. The second part is an offset, D, which says where inside that piece the data is. The system then takes that page number P and looks it up in the page table. That tells it which physical frame, F, the piece is actually stored in. Finally, it combines that frame F with the offset D to get the exact physical address in RAM. It's a quick extra step, but it makes the whole system unbelievably fast and flexible.
Okay, so paging was a total game changer. It was revolutionary. But what it did was unlock an even more powerful concept, something that honestly feels like straight-up magic. And that is virtual memory.
This is where things get really, really cool. Virtual memory is a trick, a brilliant illusion. It makes your computer think it has way, way more RAM than it actually physically has. How? It lets you use your much slower but absolutely massive hard drive as an extension of your super fast RAM.
Let's bring our valet back into this. Imagine the main parking lot. Our RAM is completely full. But our valet also has access to this huge, much slower overflow lot down the street. That's your hard drive. So what the valet can do is take the pieces of a car that nobody's using right now and move them over to that overflow lot. And that frees up prime real estate, the really fast spots for the cars that need immediate access.
Okay, so what happens when the computer needs a piece of a program that's been moved to the overflow lot, to the hard drive? Well, this event is called a page fault, and it's super important to know this is not an error. It's not a bad thing. It's just a signal to the operating system, to our valet, to pause for a split second, run down to the hard drive, grab the piece it needs, and bring it back into an open spot in RAM. And for you, the user, the whole process is so fast it's almost completely invisible.
Now, all this swapping back and forth between the main lot and the overflow lot, it sounds pretty complicated. And yeah, it can be. If you're not careful, our valet could end up spending all their time just running between the two lots instead of actually getting any real work done. So how does the system possibly stay fast? Well, this exact performance problem has a name. It's called thrashing. And that's what happens when the system spends almost all of its time just swapping pages back and forth between RAM and the hard drive. It's so busy managing the memory that it has no time left to do any actual work. The whole computer just grinds to a halt. Our poor valet is just completely overwhelmed, just running back and forth, not getting anything done.
So, this really is the million-dollar question, isn't it? To avoid thrashing, the system needs a really smart strategy. When the main lot, the RAM, gets full and you need to bring in a new piece of a car, you have to send another piece out to the overflow lot. You have to kick one out. But which one? If you pick the wrong one, you might need it again just a split second later, causing another page fault. And that brings us to the different strategies, the page replacement algorithms. First, you've got FIFO, or first in, first out. It's the simplest. Just get rid of the page that's been in there the longest. It's easy, but what if that oldest page is still super important? A much smarter way to do it is LRU, or least recently used. This one kicks out the page that hasn't been touched in the longest time. The thinking is pretty solid, right? If you haven't used it in a while, you probably won't need it again soon. It works really well, but it's a little more complex for the system to keep track of. And then there's the optimal algorithm. This is the perfect strategy. It would replace the page that won't be used for the longest time in the future. The only tiny problem? It requires a crystal ball. It means predicting the future, which, as far as I know, computers can't do. Yet. So think about that journey. We went from simple, clunky, contiguous blocks to this incredibly complex dance of pages just flying between your RAM and your hard drive. Memory management is truly a masterpiece of problem solving. It's this invisible, high-stakes ballet that makes everything we do on our computers possible. So the next time you open just one more app, remember that silent, lightning-fast valet juggling everything inside your machine. And it makes you wonder, right? What other invisible magic is powering your digital world?